We are already familiar with the thermodynamic properties, temperature, pressure, and specific volume. But now we're going to introduce three more properties: internal energy, enthalpy, and entropy. We can think of internal energy as the energy associated with a system due to the motion and potential energies of its individual particles. It's usually measured in kilojoules. Enthalpy is a property which is the sum of the internal energy and the product of pressure and volume. It is also measured in kilojoules. The final property, entropy, is a property associated with the second law of thermodynamics. Entropy is measured in kilojoules per Kelvin. Internal energy, enthalpy, and entropy are all extensive properties and depend on the size of the system. We can define the specific internal energy, specific enthalpy, and specific entropy of a system by evaluating the original properties per unit mass, and we adjust their units accordingly. Conventionally, we represent the properties using capital letters and their specifics as small letters. Now we'll go into property tables. For most substances, the relationships among thermodynamic properties are too complex to be expressed by simple equations. Properties are therefore frequently presented in the form of tables. In this video, we'll use steam tables to demonstrate how thermodynamic property tables are used. First, we're going to start with the saturated liquid and saturated vapor states. The properties of saturated liquid and saturated vapor for water are listed in both tables shown. The only difference is that in this table, the properties are listed under temperature, and in the other table, the properties are listed under pressure. It's more convenient to use the temperature table when temperature is given, and the pressure table when pressure is given. All of the thermodynamic tables show the specific properties. So we have specific volume, specific internal energy, specific enthalpy, and specific entropy. The subscript F is used to denote properties of a saturated liquid, and the subscript G is used to denote the properties of saturated vapor. So Vf is the specific volume of saturated liquid, Vg is the specific volume of saturated vapor, UF is the specific internal energy of saturated liquid, and Ug is the specific internal energy of saturated vapor. Hf is the specific enthalpy of saturated liquid, and Hg is the specific enthalpy of saturated vapor. And finally, Sf is the specific entropy of saturated liquid, and Sg is the specific entropy of saturated vapor. The subscript Fg denotes the difference between the saturated vapor and saturated liquid values of the same property. For example, Vfg equals Vg, which is the specific volume of saturated vapor, minus Vf, which is the specific volume of saturated liquid. And the same applies to other properties. Now, we are going to use the steam tables to solve some basic problems involving saturated liquid and saturated vapor. The first problem. A rigid tank contains 50 kilograms of saturated liquid water at 90 degrees Celsius. Determine the pressure in the tank and the volume of the tank. So to solve this, the liquid is saturated at 90 degrees Celsius. This means 90 degrees Celsius is its saturation temperature at this current pressure. We know its saturation temperature, so we use the temperature entry table. From the saturated temperature column, we locate the 90 degrees Celsius row, and we want to know the pressure which corresponds to this temperature. So we trace the pressure down to 90 degrees and obtain our pressure as 70.183 kilopascals. To find the volume of the tank, we trace Vf, which is the specific volume of saturated liquid, down to 90 degrees Celsius, and we obtain 0.001036 meters cubed per kg as the specific volume of our liquid at this temperature. The total volume of the liquid will be the specific volume multiplied by its mass. and we obtain 0.0518 meters cubed as the total volume of the tank. Some steam tables usually don't have entries for the specific volume of saturated liquid because the values are negligible compared to the specific volume of saturated vapor and can often be approximated to zero in calculations. So let's try another problem. A mass of 200 grams of saturated liquid water is completely vaporized at a constant pressure of 100 kilopascals. Determine 1. The volume change, and 2. The amount of energy transferred to the water. Now our solution. To find the volume change, we need to find the difference between the initial and final volume. At the initial state, the water is a saturated liquid, so its initial volume is the volume of saturated liquid. And at the final state, the water is a saturated vapor, so its final volume is the volume of saturated vapor. And the difference in volume is equal to Vg minus Vf. We can factorize the mass from both terms, and we're left with the specific volumes, which we can obtain from our steam tables. So we need to find Vf and Vg, the specific volumes, for a saturation pressure of 100 kilopascals. We'll use the pressure entry table and we locate the 100 kilopascals rule. Then we trace Vf and Vg to this pressure, and we obtain Vf, the specific volume of saturated liquid, to be 0.001043 meters cubed per kilograms, and Vg, the specific volume of saturated vapor, as 1.6941 meters cubed per kg. So Vg minus Vf equals 1.6931 meters cubed per kilogram, and our change in volume equals the mass of the mixture into Vg minus Vf, which gives us 0.3386 meters cubed. Now, to find the energy transferred to the water, we use enthalpy. Enthalpy is usually considered the heat content of a substance. So the total energy in the form of heat transferred to the water will be the difference between the final and initial enthalpy. Our initial enthalpy is the enthalpy of saturated liquid, and our final enthalpy is the enthalpy of saturated vapor. So the change in energy, or the energy transferred, is Hg minus Hf. And again, if we factorize the mass from both terms, we get mass into the specific enthalpy of saturated vapor minus the specific enthalpy of saturated liquid. And we can rewrite this as m times Hfg. From our steam tables, we can trace Hfg for this particular pressure to 2257.5 kilojoules per kg. And so our change in energy, or the energy transferred, is equal to 0.2 times 2257.5, and this gives us 451.5 kilojoules. Next, we're going to focus on using our steam tables to analyze the saturated liquid vapor mixture state. During the vaporization process, a substance exists as part liquid and part vapor. It is a mixture of saturated liquid and saturated vapor. In order for us to properly analyze this mixture at any point, we need to know the proportions of liquid and vapor in the mixture at that point. Hence, we define a new property called the quality of the mixture, X. The quality, or dryness fraction, is the ratio of the mass of vapor to the total mass of the mixture. This property is significant only for saturated liquid-vapor mixtures. We have no need for it when dealing with the compressed liquid state or the superheated vapor state. We can use the dryness fraction to determine the specific properties of our saturated liquid-vapor mixture. Let's use enthalpy. Say, for instance, we had a mixture of known temperature or pressure. The total enthalpy of the system would be the sum of the enthalpies of the liquid and vapor constituents. Remember, we use the subscript F to denote properties of liquids and G to denote vapor properties. The average specific enthalpy for this mixture would be the total enthalpy divided by the total mass. Usually, we don't have enough information to obtain this value. But if we know the saturation temperature or saturation pressure, we can easily use our steam tables to obtain the specific enthalpies of the liquid and vapor constituents, HF and HG, where HF, the specific enthalpy of the saturated liquid, equals the total enthalpy of the saturated liquid divided by the mass of the saturated liquid, and Hg, the specific enthalpy of the saturated vapor, equals the total enthalpy of the saturated vapor divided by the total mass of the saturated vapor. We can rearrange these, and now we can use them in our equation to find the average specific enthalpy. Remember that our dryness fraction x equals the mass of the vapor constituents divided by the total mass of our system. So we can write H equals HF times mf divided by the total mass plus x times Hg. But what do we do about the term mf divided by the total mass? Well, remember that the total mass equals mf, the mass of the saturated liquid, plus mg, the mass of the saturated vapor. So mf equals the total mass minus mg. And mf divided by the total mass equals 1 minus x. So H, the average specific enthalpy, equals 1 minus x into HF plus x times Hg. Expanding this, we have H equals HF minus XHF plus XHG, which gives us H equals HF plus x into Hg minus HF. Remember that we can use the subscript Fg to denote the difference between the saturated vapor and saturated liquid states. So H equals HF plus X HFG. This difference, HFG, can also be readily obtained from steam tables. Now, we've eliminated the need to know the total mass or the total enthalpies of the liquid and vapor constituents in order to find the average specific enthalpy of our mixture. All we need to know is the dryness fraction and the saturation temperature or saturation pressure of our mixture, and we're good to go. Also, this doesn't just apply to enthalpy. It applies to other properties, specific volume, specific internal energy, and specific entropy. So, V equals Vf plus X Vfg, U equals Uf plus X Ufg, H equals Hf plus X Hfg, and S equals Sf plus X Sfg. Now let's solve some problems on this. The first one, calculate the dryness fraction of steam which has 1.5 kilograms of water in suspension with 50 kilograms of steam. So we know that mf, the mass of the saturated liquid, equals 1.5 kilograms, and mg, the mass of the steam or the saturated vapor, equals 50 kilograms. So our total mass equals mf plus mg, and this gives us 51.5 kilograms. So our dryness fraction is going to be mg, which is the mass of the vapor constituent, divided by the total mass, and that gives us 0.971. Now on to our next problem. A vessel having a volume of 0.6 meters cubed contains 3 kilograms of liquid water and water vapor mixture in equilibrium at a pressure of 0.5 megapascals. Calculate 1. The mass and volume of liquid, and 2. The mass and volume of vapor. We know that our total volume equals 0.6 meters cubed. Our total mass equals 3 kilograms. And our saturation pressure is 0.5 megapascals or 500 kilopascals. We can find the specific volume or the average specific volume of our entire mixture as the total volume divided by the total mass, and that gives us 0.2 meters cubed per kg. We know V equals Vf plus X Vfg, and using our steam tables we can find Vf and Vfg at 500 kilopascals. So Vf equals 0.001093 meters cubed per kg, and Vg equals 0.37483 meters cubed per kg. Now the difference, VFG, which is Vg minus Vf, equals 0.37374 meters cubed per kg. So, substituting our known values into the equation, we have 0.2 equals 0.001093 plus 0.37374x, which is our dryness fraction. So we can solve for our dryness fraction x, and we obtain it to be approximately equal to 0.535. Now to find the mass and volume of the liquid, we know that the mass of the liquid equals the total mass minus the mass of the vapor. And dividing both sides by the total mass, we get mf divided by the total mass equals 1 minus x. So the mass of the liquid equals 1 minus our dryness fraction x multiplied by the total mass. And we obtain the mass of our liquid here to be 1.395 kilograms. Next, to find the volume of the liquid, we simply multiply the mass of the liquid by its specific volume, and we obtain 0.0015 meters cubed. To find the mass and the volume of the vapor, we know that our dryness fraction equals the mass of the vapor divided by the total mass of the mixture. So the mass of our vapor equals our dryness fraction multiplied by the total mass. And we obtain the mass of our vapor to be 1.605 kilograms. And to find its volume, the volume of the saturated vapor, we simply subtract the volume of the liquid constituent from the total volume, and we obtain 0.5985 meters cubed as our volume. Final question on saturated liquid vapor mixture states. A vessel having a capacity of 0.05 meters cubed contains a mixture of saturated water and saturated steam at a temperature of 245 degrees Celsius. The mass of the liquid present is 10 kilograms. Find the following. 1. Pressure. 2. The mass. 3. The specific volume. 4. The specific enthalpy. 5. The specific entropy. And 6. The specific internal energy. So we know that our total volume equals 0.05 meters cubed. The saturation temperature is equal to 245 degrees Celsius, and the mass of our saturated liquid present in the mixture is equal to 10 kilograms. So to find the pressure, we already know the saturation temperature as 245 degrees Celsius. We can use our temperature entry steam table to determine the corresponding saturation pressure for this temperature. Doing this, we obtain 3,651.2 kilopascals as our pressure. To obtain the mass, we know that the mass of our saturated liquid equals 10 kilograms. So the volume of our saturated liquid will be its mass times the specific volume of saturated liquid at this temperature. From our steam tables, at 245 degrees Celsius, Vf, the specific volume of saturated liquid, equals 0.001240 meters cubed per kg, and Vg, the specific volume of saturated vapor, is equal to 0.054656 meters cubed per kg. So the total volume of our saturated liquid in the mixture is its mass, 10 kilograms, multiplied by 0.001240, which gives us 0.01240 meters cubed. And the volume of saturated vapor in this mixture is the total volume minus the volume of the saturated liquid in the mixture. And this gives us 0.0376 meters cubed. Now, the mass of the saturated vapor or gas constituent is going to be equal to the total volume of gas divided by its specific volume, which we've already obtained from the steam tables. And this is 0.0376 divided by 0.054656. And so we obtain the mass of the vapor constituent in our mixture as 0.688 kilograms. So the total mass will be the mass of the liquid constituent, the saturated liquid, plus the mass of the saturated vapor constituent. And this is 10 kilograms plus 0.688 kilograms. And this gives us a total mass of 10.688 kilograms. The third property we're supposed to find, the specific volume. So for this, we can use V equals Vf plus X Vfg, or 1 minus X into Vf plus X Vg. Now, our dryness fraction, F, equals the mass of the vapor constituent divided by the total mass of our fluid, which is 0.688 divided by 10.688. And this gives us 0.064. So, our specific volume, V, 1 minus 0.064 times 0.00124 plus 0.064 times 0.054656. And we obtain our specific volume to be 0.004659 meters cubed per kg. For our specific enthalpy, we use H equals HF plus X HFG. And from our steam tables, we obtain HF as 1061.5 kilojoules per kg and HFG as 1740.8 kilojoules per kg at this saturation temperature. So our specific volume H equals 1061.5 plus 0.064 times 1740.8, and we obtain 1172.9 kilojoules per kg as our specific enthalpy. Next, to obtain our specific entropy, the calculation is similar to what we just did. So S, which is the specific entropy, is equal to SF plus X SFG. So from our steam tables, we obtain SF to be 2.7476 kilojoules per kg Kelvin, and our SFG as 3.3596 kilojoules per kg Kelvin. So our S specific entropy equals 2.7476 plus 0.064 times 3.3596, which equals 2.9626 kilojoules per kg Kelvin. And finally, for our specific internal energy, we do the same thing we did previously. U equals UF plus X UFG. So from our steam tables, UF equals 1056.9 kilojoules per kg and UFG equals 1545.7 kilojoules per kg. So our specific internal energy U equals 1056.9 plus 0.064 times 1545.7. And this gives us 1155.8 kilojoules per kg. Finally, we are going to use our steam tables to analyze steam in the superheated state. Our substance exists as a superheated vapor to the right of the saturated vapor line and at temperatures above the critical temperature. The superheated water table shows the properties of superheated vapor for different temperatures at certain pressures. So here we have a pressure of 0.05 megapascals or 50 kilopascals. And beside it is the saturation temperature at this pressure, which is 81.32 degrees Celsius. This means water boils at 81.32 degrees Celsius at a pressure of 50 kilopascal. The first row shows the properties at the saturated vapor state, and the rows that follow show the properties at higher temperatures. We can see that there is no entry for 50 degrees Celsius because 50 degrees Celsius is less than the saturation temperature, 81.32 degrees Celsius. And so at this temperature, our substance is a compressed liquid. The next row shows the properties of our substance at 100 degrees Celsius. And of course, 100 degrees Celsius is higher than our saturation temperature, so the substance is superheated at this state. The other rows follow in the same manner, showing us the properties of superheated vapor at higher temperatures. Now let's solve a problem on the superheated vapor state using our steam table. Calculate the internal energy per kilogram of superheated steam at a pressure of 10 bar and a temperature of 300 degrees Celsius. Also, find the change of internal energy if this steam is expanded to 1.4 bar and a dryness fraction of 0.8. And to solve this, internal energy per kilogram simply means the specific internal energy. We know our pressure is 10 bar or 1 megapascal, and our temperature is 300 degrees Celsius. So we use our superheated water table and we check 300 degrees Celsius under 1 megapascal. The specific internal energy of our vapor is obtained to be 2793.7 kilojoules per kg. Now we're told the steam is expanded to 1.4 bar or 140 kilopascals and has a dryness fraction of 0.8, which means it is a saturated liquid vapor mixture at this state. So our internal energy U equals UF plus XUFG. On our saturated vapor table, we don't have 140 kilopascals, but the two closest pressures to that value are 125 kilopascals and 150 kilopascals. So we have to use a linear interpolation. Now at 125 kilopascals, UF equals 444.23 kilojoules per kg, and UFG equals 2068.8 kilojoules per kg. And at 150 kilopascals, UF equals 466.97 kilojoules per kg, and UFG equals 2052.3 kilojoules per kg. The interpolation works based on the proportions of the difference in values. So on our left-hand side, we have 140, which is the desired pressure, minus 125, divided by 150 minus 125. And on our right-hand side, we have the corresponding values of specific internal energy. So on the right-hand side, we have UF, which corresponds to 140 kilopascals and is unknown, minus 444.23, which corresponds to 125 kilopascals, divided by 466.97, which corresponds to 150 kilopascals, minus 444.23. From this, we get UF at 140 kilopascals as 457.87 kilojoules per kg. And we do the same thing for UFG. So we obtain UFG as 2058.9 kilojoules per kg. And then we can use these values we've obtained for UF and UFG in our equation to find the specific internal energy. So U equals 457.87 plus 0.8 times 2058.9. And we get our specific internal energy as 2104.99 kilojoules. The difference in specific internal energy, therefore, is 2793.7 minus 2104.99. And this gives us 688.71 kilojoules. This means there is a drop in internal energy as the vapor goes from the superheated state to the saturated liquid vapor mixture state.